drone to process these various visual inputs during its flight time. I'd now like to pass it on to Ronald, who will be speaking more on the drone's software.
So in order to power the drone, we use Python as our programming language. It's a high-level language that is commonly used in computer vision projects. In order to actually implement the computer vision, we use the library called OpenCV, which enables us to detect the target object. Now I'll pass it on to Alex, who will be talking to us more about the existing computer vision algorithm.
Now, masking technique is crucial to the overall object detection of the drone, where by using masking, we can completely remove the background of an image. By inputting specific HSV values, you can see in this photo that the background is completely removed and only the tennis ball is seen. Now, after masking, the algorithm detects contours, or the edges of an object, and it encapsulates the object in a bounding box. Where in this image, you can see how even though there's a multitude of different colors in the background, the object is still being tracked because of the masking technique used. Now, object detection is also crucial to the position determination of the drone, where the drone determines an object's position relative to itself by using the three variables rho, phi, and beta, where rho is the absolute distance, phi is a position angle, and beta is a yaw angle. And these three values are continuously being calculated through trigonometric values and similar triangles. However, through our testing, we found that phi, the position angle, was flawed in its accuracy, and the development of a new method of tracking was needed. Now I'll pass it on to Chelsea to talk about Priorworks.
So because this is an existing project, one of the first things that we decided to do was to determine the limitations and capabilities of the existing system. And we found two things that we thought we could address. The first was that there was a slow response time to the drones, the moving position of the object of interest, which the video isn't working right now, but that's what the video was of. And we attributed this to a low processing frequency, which we decided to improve through our research. And the second thing was that though the drone had basic position and distance tracking capabilities, it was not precise enough for it to be able to dock onto a moving docking platform. So we also decided to focus on this for our research. Now I'd like to pass it on to Ronald for procedure.
So for our procedure, we replicated the drone's processes by integrating its hardware and software together, which was Raspberry Pi, computer vision, and Pixar flight controller. Now we couldn't get the Raspberry Pi and Pixar flight controller working together, so instead we shifted our focus onto just running the computer vision tests on the Raspberry Pi and seeing how well it would perform on that device. We needed benchmarks to quantify the performance of the computer vision algorithm and find areas for improvement, so we ran 3 different tests, which we'll be describing more in the following slides. So the first test that we ran was the frequency test. Its goal was to measure the computer vision performance by figuring out how long it took to run specific parts of the code, specifically how many iterations it could run per second, or putting it in hertz. So we added a bit of benchmarking code to the computer vision program to calculate the time it takes to run 2 parts within. First was the process frame method, and that part of the program runs all the computer vision algorithms to detect the object and calculate its distance from the camera. The second part was the main loop, and that calls process frame. It also reads from the camera input and sends commands to the flight controller. So after running the control test, we reworked the algorithm to decrease the frame size by having its dimensions to see if that would increase its performance. The frequency test was then rerun for both parts of the program. So for our results, we saw that when we decreased the frame size by half, the process frame method resulted in a processing frequency increasing by 222%. This large increase is likely attributed to the fact that resizing the frame's dimensions by half meant only that a quarter of the pixels need to be processed, and that definitely sped up the process of detecting the object using the OpenCV algorithms. On the other hand, we saw that for the wild loop method, there wasn't much of an improvement. It was just 5.46%. And that might be due to the hardware restrictions that capped the speed of the process. Because we were using a Logitech camera that records at only 15 frames per second, that meant that we couldn't achieve a processing frequency above 15 hertz. Now I'm going to pass it on to Chelsea, who will be talking to us about the distance accuracy test.
So in order to determine the accuracy of the script's row value calculation, we decided to conduct a distance accuracy test. And the basic setup for the test was connecting a camera to a Raspberry Pi and setting the tennis ball a distance away from it and increasing the distance in increments. And then we ran a script that would output the distances measured. And so at first when we ran this test, we didn't calibrate the focal length of the camera, and so we got undesirable results. After calibrating the focal length of the camera, we got more desirable results, which Karina will talk about in the next slide.
The evaluation of this distance accuracy test was conducted by comparing how close the calculated rho value was to the actual distance between the drone and the object, which in this case was the tennis ball. And so as you can see on the graph to the left, the blue trend line depicting the initial data we collected with the non-calibrated focal length produced quite a bit of error, and it was quite off from the actual distances between the camera and the tennis ball. However, we tried to resolve this issue by now calibrating the focal length and adjusting it into this new distance tracking algorithm. And as you can see, the rho values that were now being produced yielded a new trend line that was actually quite accurate and quite similar to the perfect actual distance trend line. I will now pass it on to Alex, who will be speaking on horizontal position accuracy test.
So because the horizontal position tracking was inaccurate in its testing, we needed a new method to determine horizontal position. And we did this by measuring the distance of the tennis ball and dividing it over the space it took in pixels. We then multiplied it by the distance it was away from the center of the screen. And we measured the accuracy of this, and in our measurements, we found that the slope of our data was 1.0077, which showed it was very accurate to a perfect slope of 1, which indicates perfect accuracy, showing that our method was viable to use. I'll pass it to Karina to discuss our conclusions now.
So, through the benchmarking test that we were able to conduct throughout the duration of our research, we were able to receive a quantitative analysis of the computer vision's performance. And we also learned that while the previous code was effective in basic object detection and tracking, it really did lack in its ability to enable the drone to redock onto the docking platform. And so to address this issue, we created 3 tests: the frequency test, the distance accuracy test, and horizontal position accuracy test to address these issues. With the frequency test, we were able to show considerable improvements to the speed of the visual input processing. However, there were some restrictions drawn with the hardware specifications of the camera. With the distance test, we were able to show that recalibration of the camera's focal length would be needed in order to produce these accurate rho values. And finally, with the horizontal position accuracy test, we were able to present a new method of finding the horizontal distance between the drone and the tracked object. However, in the future, we definitely like to take this project to the next level by testing in a real-life environment.
We don't have any more time, but thank you for presenting.